Good afternoon, sir. This is Naveen from NPTL.
Oh,
There's only one question in forum.
okay,
I'll just copy and paste it here in the chat box. Uh, I think you can start the session with that question, sir.
okay. Where is the question? Have you given the question?
Yes, sir. 1 minute, sir. I'm copying and pasting it. Yes, sir. I have pasted the question. You can start the session with this question.
Mm. How we differentiate doublet and triplet from graph? Okay. I don't know whether that person is Abhinandan is online, but anyway, I will start giving the answer for that. See, doublet will be always two lines of equal intensity, and then the separation of these two peaks gives rise to what is called J coupling. See, if I have a doublet like this, measure the separation between these two in frequency that correspond to J coupling. Whereas triplet means three lines will be there of intensity 1:2:1. Outer two lines of equal intensity of 1. Central line will be one line of two intensities. It is a 1:2:1 triplet. In this case, any separation between one line to next adjacent line correspond to J coupling. Similarly, central line to rightmost line correspond to J coupling. So triplet is actually three lines of intensity 1:2:1. Doublet is two lines of equal intensity. I hope you understood. This is what I think that's your question is. That's how you have to differentiate doublet and triplet. Okay. I hope what the answer I gave is clear for people. Abhinandan, I hope it is clear for you. So any other question from anybody? Aravindan has joined. Aravindan, you have any question?
No, sir. Just now joined. Thank you.
If you have any specific questions, specific doubts to be clarified, please ask me.
Okay, sir.
Arindam Gogoi has joined. Arindam, do you have any specific question? Ravindan, do you have any specific questions? Any doubts?
Sir, no, sir. No, sir. I don't right now. Shall I use?
No, up to you. If you have any specific question, you can ask me. So how are you following this course? Is it
Yes,
useful for you? Are you able to learn something?
yes, sir. Yes, sir. I can able to. But the
Okay.
thing is, assignment questions somewhat I felt tougher.
It tough for you.
Yes, little.
Okay, I will ask our TA to post the question answers to all these things.
Okay,
Okay,
sir.
all the assignment answers we will post it soon. After the course is over, we'll post it.
Okay.
And of course, if you want to learn more about the interpretation, everything,
Yes, sir.
that a lot more things with see, this was only online where recorded version was there. From
Yes, sir.
23rd of this month, coming Monday, in the same NPTL Plus platform, there is a workshop being done by me.
Okay, sir. Okay, sir.
That is go to NPTL Plus platform, NMR workshop. I am conducting 1 week workshop. In the evenings, I am
Okay, sir.
giving lectures where I am giving a lot of examples, and you can personally seeing, you can discuss, not recorded one. So online. So if you like, you can register for that. You go to
Okay,
NPTL
sir.
website, NPTL
Okay,
Plus.
sir. Okay, sir. Okay, sir. Sure,
There
sir.
you
I
will
will
see
do.
NMR workshop coming from 23rd. It is going to start.
Okay, sir. I will do that.
Okay, very good.
Sir, and there is two more question in YouTube. I have
Hmm.
copied and pasted in this chat box.
Okay, let me check.
Asked by Cyril Raj.
Okay, I'll see that. Okay. See, Cyril Raj has asked a question: how to write transition for a given set of nuclei? See, you must understand each nuclear spin has two possible orientations. That is alpha and beta. These two are two energy states. If I consider two interacting spins, each has alpha beta states. For example, A and X. A has alpha and beta, X has alpha and beta. Now, what will happen when these two nuclear spins are interacting? If A is like this, X can also be like this, or X can be like this. If A is like this, X can be like this, or X can be like this. That means there are four possible combinations of orientation of the two nuclear spins. That means we have each of them is a particular energy state, correspond to particular energy. Now we have four possible orientations for two spins. And this is corresponding to four energy states. You can write like this. If this is alpha, this is alpha. It is called alpha alpha. If this is alpha, this is beta, alpha beta. This is beta, this is alpha, beta alpha. Both are down like this, beta beta. So 4 energy states are there. Now, for each of these energy states, you can write what is called magnetic quantum number. What is magnetic quantum number? It is sum of the individual eigenvalues of each individual spin. For example, alpha alpha. Alpha corresponds to half. Beta corresponds to minus half. Alpha alpha means you have to take the sum of these two, half plus half. So total magnetic quantum number for alpha alpha state is 1. You go to alpha beta state. Alpha is plus half, beta is minus half. If you take the sum, what will happen? It will become 0. Go to another one, beta and alpha. That is also minus half, plus half. That is 0. Go to 2, both down, minus half, minus half. That is minus 1. So totally, you have 4 energy states. The magnetic quantum number, magnetic energy for each of the states can be represented by, okay, total magnetic quantum number, plus 1, 0, 0, and minus 1. Now, your question is, how to write the transition for a given set of nuclei? For example, if you come to alpha alpha to alpha beta, alpha alpha is plus 1, alpha beta is 0, and magnetic quantum number is 0. Plus 1 to 0 is an allowed transition because according to the selection rule, transition between any two energy states whose difference in the magnetic quantum number either plus 1 or minus 1 is allowed. This is called the allowed transition. This is a selection rule. So plus 1 to 0 is allowed. You can write as one transition. Similarly, plus 1 to another 0 is also there. This is alpha beta and beta alpha. That is also allowed. Minus 1 to alpha beta, that is beta beta to alpha beta, that is allowed. Beta beta to beta alpha, that is also allowed. Because in each of these cases, plus 1 to 0, difference is 1. Plus 1 to another 0 is 1. Minus 1 to 0 is also minus 1. So if any of these two, any of these transitions are allowed because the change in the magnetic quantum number between these two energy states is either plus 1 or minus 1. So now how many transitions are there for AX spin system when two spins are coupled? You have 4 transitions. Okay, we saw that alpha alpha to 0, alpha beta, alpha alpha to beta alpha, that is allowed, beta beta to alpha beta, and beta beta to beta alpha. So 4 transitions are allowed for 2 spin. Now if you go to 3 spin, you ask the question A, M, and X. Now you consider the possibilities. When you have 2 spins, alpha alpha, alpha beta, beta alpha, beta beta, 4 possibilities. Now you take the another one. The X spin can have alpha beta. So what will happen? This alpha alpha, each of these 4 now become 8. The 4 transitions, 4 energy states become 8 because each of these 4 energy states can have X nuclei in the alpha state, can have X nuclei in the beta state. So alpha alpha is now with the X nuclei, it becomes alpha alpha alpha, beta alpha becomes beta alpha alpha, alpha beta becomes alpha beta alpha, beta beta becomes beta beta alpha. This is for alpha spin state of X nuclei. What happens to beta spin state? Same for you right now. Alpha alpha, beta, alpha beta, beta, beta alpha, beta, and then beta beta beta. So there are 8 energy states. Remember, alpha 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 and beta 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 correspond to plus 3 by 2 and minus 3 by 2 is the total magnetic quantum number for each energy state. For the remaining, what will happen? For example, if you take alpha beta alpha, this becomes plus half because half minus half plus half. If you take the sum of these three, it becomes plus half. Similarly, beta alpha alpha is plus half. Similarly, beta beta alpha, if you take, it will become minus half. Now you look for the other four energy states for beta orientation. So you can find out, now you have 8 energy states, and top one alpha 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 for 3/2, beta 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 is minus 3/2, and the remaining 6 energy states, 3 of them will become equal, correspond to plus half, and the 3 of the remaining become equal, correspond to minus half. Now we can find out what are the allowed transitions for each of them. Plus 3/2 to minus half, difference is allowed, and 3/2 to plus half, minus 3/2 plus half is allowed, plus half to minus half is allowed. All these combinations you can think of transitions. AMX that way will give rise to 8 transitions. I'm sorry, 4 plus 4 plus 4. Each nuclei gives 4 transitions. 4 plus 4 plus 4 for 8 energy levels. You have 12 transitions. I hope you understood. There are 12 transitions for 3 spins A, M, and X, weakly coupled. I hope you understood. Anybody else? So Cyril has left. So Arvindam, there is one more person. His name is not shown here. It is showing us dot. I don't know who is that. Avinash, do you know who is that?
No, sir, I don't.
He has only put a dot. I don't know who is it. If he can answer since I don't know his name, he or she can ask the question if you have any doubt. The participant, your name is not displayed here. Please ask the question or doubt if you have any. There is one question. Okay. Sir, will the number of transitions for strongly coupled twin system varies? Or will it be same? No. This is a very good question. I don't know who asked this question. Okay, the person, I don't know. Can you please write your name? I want to know who is that. Okay, so your question is very good. Weakly coupled and strongly coupled always need not have the same number of transitions. Of course, except for two spins. For example, two coupled spin system can be AX, AB, and A2. AX is weakly coupled. You get 4 lines, 2 for A, 2 for X of equal intensity. Okay, that is 4 line. AB is strongly coupled because chemical shift difference between A and B is very, very small. They come very close by. But the coupling is also comparable to chemical shift separation. It is strongly coupled. But still you have 4 lines. 2 strong lines at the center, 2 weak lines outside. Still you have 4 lines. But only difference in this case is the intensities are not equal like AX. Weakly coupled AX, all 4 lines are of equal intensity. In the case of AB, 2 central lines are of same intensity, 2 outer lines of same intensity. There is enormous difference between intensity of the central line and the outer lines. And this intensity difference between these two keeps on increasing as this chemical shift difference becomes smaller and smaller and smaller. What will happen? That the chemical shift difference between these two becomes 0. There is no difference at all. What do you call this? This is called A2 spin system. AX becomes AB. Still, there is chemical shift difference between AX and also between A and B in AB. When you come to A2, there is no difference in chemical shift. So, they are equivalent spins. In A2, you have how many peaks you get? Only one peak you are going to see. In reality, it is not one peak. It is 2 peaks of 2 different transitions overlap. So AX will give 4 pair transitions, AB will give 4 transitions, whereas A2 will give only 2 transitions which are overlap. As a consequence, you get a single peak. That's fine. Now we'll go to a 3 spin. In the case of 3 coupled spins, for example, weakly coupled, A, M, and X. Letters are far away separated. That means they are weakly coupled. In the weakly coupled case, AMX, you get 4 for A, 4 transitions for M, and 4 transitions for X. You get only 12. But I told you in the class, if you remember, if there are n number of spins coupled, the number of transitions are always given by 2nc n minus 1. For 3 spins, there must be what is called 15 allowed transitions. What are these 15 allowed transitions? As I told you, 4 for A, 4 for M, 4 for X, and weakly coupled. But let us go to what happened to the remaining 3 transitions, you may ask me. They are called combination transitions, which are very, very weak in intensity. So in weakly coupled, you will not see that. Whereas if you go to the strongly coupled case, like AMX becomes, let us say, ABC, you will see all the 15 transitions. These 3 combination transitions are also seen. See the difference now? Your question is, will the number of transitions are same for strongly coupled and weakly coupled? Same 3 spin, I took the example. For AMX, we have 12 transitions. For ABC, we have 15 transitions. Transitions are different. Intensity pattern is different. Same way, you go to 3 spin, AB2, you go. AB2 will give you 9 lines, 9 peaks. So that's what the difference is. Weakly coupled and strongly coupled, number of peaks detected or observed will be different, depending upon chemical shift difference between them and also coupling strength. That's the important point you should remember. So, but total number of peaks cannot exceed, according to the formula, 2n c n minus 1. You got the point. So for 3 spins, there are maximum 15 lines. For 4 spins, maximum 56 transitions. All 56 you will not be able to see. For 4 weakly coupled, you are going to get each of these things will give 8 lines, 8, 8, 8, 8, 32 lines you will see. But if it becomes very, very strongly coupled, like AA prime, double prime, triple prime, or ABCD, you may get few more additional transitions of weak intensity. That's all the difference. So basically, the answer to your question is the number of transitions for strongly coupled and weakly coupled need not be same. Except, for example, in the case of AX and AB, total number remains the same, number of transitions, the intensities are different. Same way, you can understand for 3-spin, 4-spin, etc. I hope it is clear for you. Since you are not switched on the mic, please at least respond whether it is clear for you. Clear, sir. Okay. Can you identify yourself? What is your name, please? Because your name is not displayed here. Cyril. Oh, okay, Cyril. Okay. Very good. Any other questions? Hi, Sandeep. How are you?
I am good, sir. How are you, sir?
You look very smart today. You are very happy, huh? Good. So how is the manuscript book? Is writing is going on?
Tonight I will send you first draft.
Huh?
First draft I will send you tonight.
Oh, very good. There is no other person who's asking questions. Cyril, you have any other questions? So how is your work, Sandeep?
Nothing, sir. Just going on.
Going?
Uh,
Very good. So Naveen, what do we do?
If at all there is no question, we can wind up, sir.
So no other question. And there are no other participant except Cyril. If Cyril
Yes,
has no questions, I think there is no point in waiting. We can log off.
Okay, sir. Cyril, do you have any more questions?
Oh, Cyril has, sir, you worked number of transitions for AMX and we got 12. How did you get 15 transitions, he says. Okay. The 15 transitions, you asked me a question, please, I'll share the PowerPoint and show you how we get 15 transitions. Don't wind up, Naveen. He has a question, I'll answer.
Yes, sir. Please continue.
Okay, Cyril, you see this what I'm going to explain now. You were asking for how we got 15 transitions, right? Now you see for 3 coupled spins, let us say I have 3 spins, 1, 2, and 3. We have 3 chemical shifts and 3 J couplings, 1, 2, 1, 3, and 2, 3. I can work out possible spin systems for this. Okay. What are the possible spin system? It could be AMX, ABX, AX prime, AX2. What is this? This is coming now in the way. Okay. And then ABC. There are 10 possible spin systems for 3 coupled spins. And each of them I have given you here. Chemical shift. For example, AMX, chemical shift 1, 2, or 3. A, M, and X are different. ABX, again they are different. AX, X prime, if you consider, 1 is different from 2 and 3. 2 and 3 are same. Like that, various combinations you can think of. Okay. Now, I will write down the energy states and transitions for 3 weakly coupled spins. A, M, and X. There are 3 possible orientations for alpha, alpha, alpha. All 3 spins can be up like this. Then, if you take the total magnetic quantum number, half, 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 it will become 3 by 2. Similarly, if it other possible states, alpha, alpha, beta, this will become plus of, minus of, is plus of. Like that, you can have 12 possible energy states corresponding to 12 possible orientations of 3 nuclear spins. Each of them has alpha and beta. Find out all possible combinations of orientations. You are going to get 8 energy states. 8 possible orientations means there are 8 different energy states. Okay, I have written like this, energy states. Alpha, alpha, this is beta, 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 all are down. Alpha, 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 all are up. This corresponds to plus 3 by 2. This corresponds to minus 3 by 2. I'm taking a weak coupled case. Then you can get transition X, this transition X, this is X, and this is X. All 4 blue transitions correspond to 1 spin X. Now red, if you consider, this is our A. The difference you can always see. See, 3 by 2 to half is difference is 1. Always the transition occurs when the energy state total magnetic quantum you calculate and take the difference, it should be either plus 1 or minus 1. This is allowed, plus up to minus of, this is allowed. Now similarly for the other one, 4 possible transitions. So totally each spin 4, 4, and 4. There are 12 transitions. Now we'll go to, okay, this is a, come to a situation like this. This is what is called combination transitions. Remember, in each of these things, only one spin was changing like this. Alpha to beta or beta to alpha, only one spin was changing. Whereas, in the combination transitions, multiple spins can flip, provided again the difference in the magnetic quantum number should be either plus 1 or minus 1. Think of this now. These 3 are allowed, plus of minus of. All beta, alpha, alpha can go to alpha, beta, beta. This is a combination transition. This is a combination transition. And this is a combination transition. These transitions are very, very weak in intensity. Okay. And these combination transitions do not contain information about J coupling. It contains only chemical shift information. 3 peaks you are going to get at some difference of the chemical shifts. And they are very weak in intensity. You are not going to see that in weakly coupled AMX. Whereas you are going to see that in the strongly coupled case. For example, these 3 transitions come at the difference of the frequencies like this. Plus X plus M plus X minus A plus A plus M minus A. Like that, it comes at some difference of the transitions. So this is how 3 transitions extra will come, which you don't see in weakly coupled AMX. But you are going to see this in strongly coupled ABC, AB2, etc. Okay, and this contains no J information, very weak in intensities, and you see only strongly coupled case. That is why AMX will have only 12 transitions. ABC, all 15 you are going to see. These weak transitions are also seen. Is it clear for you, Cyril? Cyril? Is it okay for you?
Yeah, he replied.
Okay. See, Siri has written yes, sir. Okay. He understood. How did we get 15 for ABC? I have explained to you. By diagrammatically, you understood, right? Very good. So it is clear for you how we got ABC 15. Remember, ABC will have 3 combination transitions. Your next question is whether the combination transition applicable to weakly coupled. Of course, it is there, but you don't see it. In the weakly coupled, the combination transitions are so weak in intensity, you will not see it. Only in the strongly coupled, these peaks are seen. Totally for a n coupled spin system, you have 2n, Cn minus 1 transitions. So 3 spin should give 15 transitions, irrespective of the fact whether AMX or ABC. But only thing is these are so weak in intensity, you will not see in weakly coupled. You will see it only in the strongly coupled case. Is it okay? Clear? Okay. If you have any other question, you can ask. No more questions from my side. Okay. Done. So what do we do, Naveen? Naveen? Naveen, are you there?
Yes, sir. Yes, sir. Yes, sir.
You are there. Okay, so what do we do? Now I think there are no more questions from Cyril. Should we end the show?
So, okay, sir. I'll make N for everyone.
Okay.